Yeah, it's my great pleasure to introduce Professor Sid Redner. And people who joined this meeting probably know him very well. He made like a lot of contributions in broad range of problems in non-equilibrium statistical mechanics. And yeah, aside from his research, he's a great like teacher and also a great presenter. And there are some personal connections. So I was his graduate student, PhD student, and I think Professor Hyungkyu Park, maybe he joined or not. He joined. He was his postdoctoral. Oh, there's Hyungkyu. Yeah, he was his postdoctoral researcher and Professor Byung-Nam Kang. I don't know if he joined.
Hi, Hyungkyu.
Yeah.
Yeah, so Professor Redner has quite a few Korean connections. And yeah, I have a 1 year overlap with Professor Parkman. He was a postdoc at CIS lab. And yeah, now I do more biophysical research, but the PhD time was like formative years for approaching problems. So not only specifics in certain questions, I learned, the attitude and strategy of like tackling problems. And among many things I remember, there was a quite useful advice that I got. So in one day he mentioned to me this approach called KISS, and there's nothing romantic or anything. It's keep it simple and stupid. So that's I think, one of the guidelines in approaching complex problems. So today he's going to talk about an interesting problem, I guess. And let's welcome Professor Redner.
Okay, well, thank you very much. Excuse me, this is my first time giving a Zoom talk. I've tried to avoid it as much as possible. So if you have a question, I know that there is a chat function, but I mean, I don't mind if someone shouts out a question while I'm presenting. So I'd like to talk about a very simple problem, which is inspired by the fact that sports statistics now are so readily available. And it's fun to then just analyze some very simple questions about sports statistics. So I want to talk about a very simple problem, and it's the following: is basketball scoring described by a random walk? And so this work is in collaboration with a former PhD student, Alan Gable, and Marina Kogan and Aaron Clausette from the University of Colorado. So for those of you who do not care at all about basketball, that's fine. All you need to know about basketball is that it's a competitive sport with a lot of scoring. And so there's a lot of statistics with which one can analyze the sport itself. So the thing is that for the average American, at least, when they see basketball, they see something that might look like this. If I can make my slides go forward. Yes, let me turn down the sound a bit. So this is what most people see. So it's just amazing athletic ability. People jumping up, the rim is at 10 feet above the ground. They're pushing the ball from above into the rim. They're doing unbelievable athletic activities, things that I could never dream of doing. It's just amazing what these guys can do. And so the average American is very much enthralled by these sorts of feats of athletic strength and athletic ability. And there's one drunk that's coming up in just a moment that's really worth watching. The next one, because they just break the glass in the backboard. So that is what basketball looks like, I would say, to the average American. But what it looks like to me is the following. nothing more than flipping a coin over and over again. Team A scores, team B scores, team B scores again, team A scores, team A scores. And what I'm going to try and convince you of is that basketball scoring is nothing more than flipping a coin over and over again, roughly 100 times, and the outcome of those 100 coin flips will tell you the score of a basketball game. So that is the main message of this talk. So to give you a flavor for what's going on, let's look at the score evolution in a typical NBA basketball game. And by the way, can someone tell me, is my audio okay? Is it too loud, too soft? Oh, okay. Okay, no one's complaining. Okay. Anyways, so here is a typical example. And can everyone see my mouse? Okay.
Yes.
So here is, I'm plotting the score difference as a function of time in the game. A basketball game in the National Basketball Association, which is the top league in the United States, lasts 48 minutes or 2,880 seconds. So the game starts out 0-0, and then teams start scoring baskets. And in this particular game, Denver raced out to a huge lead. So you see that the score difference is in favor of Denver over much of the game. And then somewhere close to the end of the game, Chicago mounted a furious comeback, and then Chicago's in the lead, then Denver's in the lead, Chicago's in the lead, and finally at the last minute of the game, Denver won the game. And so the question I want to ask, is this process a random walk? So that's the entire talk, is just to understand whether this is true or not. So let's look at the data and just get a feeling for like the kinds of things that happen in a basketball game. So the first thing about basketball is that you have to attempt a shot within 24 seconds of having possession of the ball, or else you lose possession. So there's a strong incentive that you cannot wait more than 24 seconds before you try and score. So if one looks at the scoring rate, which is like the probability of scoring at every single second of the game, one sees something which very roughly, and don't take this terribly seriously, but very roughly is almost constant at about 0.033, which corresponds to roughly one score every 30 seconds. So throughout the game, there is more or less constant scoring going on. So that would be the first piece of evidence to say that there's some kind of an unbiased random process that's governing basketball scoring. Another feature is the time intervals between successive scores. And I want to try and argue to you that these are not correlated. So what I'm plotting here is logarithm of the probability of a scoring interval of delta TE, where delta TE is the time between successive scores for either team. So every time there's a score, you mark on the clock that there was a score at 30 seconds, then another score at 45 seconds. That's a 15-second interval. And I'm computing the probability distribution of those time intervals. And this is on a semi-logarithmic plot. And what one sees is that, first of all, for times less than about 30 seconds, there's some anomaly going on, because once a team scores, it takes a finite amount of time to push the basketball to the other side of the court. So there's a small probability of scoring. But once you get beyond about 30 seconds, it fits beautifully just a simple exponential, which is what a Poisson process is about. And if one looks at just single team scoring, so I only look at team A scoring and the time intervals between team A scores, it's the same as either team scoring, but just changed by a factor of 2 in the overall time scale. So the time interval between scoring events appears to be Poissonian. So that's one useful piece of evidence. Another interesting thing is the feature of no correlations or no hot hand or no cold hand in basketball scoring. This is actually a very controversial subject that was first discussed by these three authors, and very famous authors in social psychology. And the point was that if any of you play basketball, you might have a feeling, well, I'm really hot right now. Give me the ball because I'm going to sink the next 10 shots in a row. And that's known as the hot hand. Do you have a hot hand, or is it just what you see from random fluctuations? And what they tried to argue in basketball scoring is that there is no hot hand. And so we looked at that same process, but instead of just having a little amount of data, which these guys had. We have 10 seasons of NBA basketball scoring, every single scoring event. We have the full data, and so we have a nice rich data set with which to analyze. So let's look at the correlations between successive scoring events. So each one of these vertical lines is meant to represent a scoring event, and T is the average time interval between successive scoring events. So if the scoring events happened regularly, then we would have equally spaced times. So if a team was hot, we would expect that the scoring events would happen very quickly, one after the other. And if a team was cold, the time interval between scoring events ought to be very long. So we can try and quantify whether a team is hot or cold by measuring the difference between the time interval to the average time interval. So let's look at this difference between the average time interval and the true time interval. And so if a team is streaky, that is, it's either very hot or cold, if it's very hot, then the time del TK will be very small compared to the average. And so this will be very negative. If a team is cold, this will be a very positive number. So this number, delta TK, should be large in streaks and small if there's no streaks. And moreover, these time intervals should be correlated when K and J are close. So if I look at successive times between scoring, if a team is hot, then I'll have two short events. And if a team is cold, I'll have two long events right next to each other. So the natural way of trying to quantify this is by looking at the correlation function of the delta TKs, the time intervals. So let's look at that. So let me define the correlation function, which is just the product. I take the product, time interval, the kth time interval, and the time interval n events down the road. And I ask, how does this function decay with n? And this type of correlation function, which we often encounter in condensed matter physics, we'd like to say that it's going to decay in some way at n, and we'll analyze how it decays. But in this particular case, there's nothing to measure because this correlation function drops to essentially 0 after one interval. So, and the blue is for either team scoring, the red is for single team scoring. So it shows that there's basically no correlation between successive events. Another thing which is perhaps more simple and more immediate and more familiar to almost anybody who studies random walks is looking at the variance in the score difference. So what I'm plotting on the y-axis is the difference in score between team A and team B squared. So it's just nothing more than x squared in a one-dimensional random walk. And I'm plotting it versus time. And one sees that this variance is growing linearly with time almost throughout the entire game. And this is sort of the very first thing that when we're exposed to random walks, we learn about is that the mean square displacement grows linearly with time. So this is a nice piece of evidence that what we're seeing is a random walk phenomenon. So the preliminary conclusion from this part of the talk is that basketball scoring looks like a random walk. But now let me turn to some more detailed aspects about basketball scoring that both provide more evidence that it's a random walk and also provide some very beautiful and surprising features about diffusion and random walks.
May I ask a question?
Yeah, please.
Well, if you measure the correlation function for each player instead of a team, does it look also like an exponential function?
Well, okay, so we do not have the data for each player. What we have is, the data set that we have is basically, there's a time trace of the game, and then there's just the score at every single second of the game. We do not have the evidence. We don't have the data for individual players. And in fact, I think that people are now looking at that to look at whether or not there's a hot hand of individual players, but we just don't have that data.
I see. Thank you.
Sure. Okay. Anyways, so more evidence for random walk behavior. So what I want to look at is the statistics of lead changes, because as I'm going to try and argue to you, lead changes are a very beautiful aspect about random walk theory that lead to some beautiful insights. And moreover, that's the most interesting part of the game. If the lead is changing all the time, then you might be interested to stay and watch the game. Whereas if one team is leading by 40 points, then you probably wouldn't bother watching anymore. So let's ask a number of very simple questions, like how many lead changes occur in a game? How long does one team lead? You know, when does the last lead change occur, and when is a lead safe? And the last one is perhaps interesting if you want to be betting in real time on a basketball game. Okay, so let's first of all look at the number of lead changes. So again, I'm plotting score difference as a function of time, and the red dots are noting the places where the score is tied, and that's where a lead change is going to occur. So we want to count the number of these red dots. So what I would argue is that if the teams are evenly matched, and if they were doing nothing more than random walk motion for the evolution of the score, the number of lead changes M would be proportional to the square root of the number of scoring events in the game. And in a typical NBA basketball game, the typical score is like 110 to 100. Each score typically is worth 2 points. That means that there's roughly 100 scoring events in a typical basketball game. So if N is 100, then we'll get like of the order of 10 lead changes. Now, why is M proportional to the square root of N? And so let me just show you why that's true. So let's look at the probability distribution of a discrete random walk in the large N limit. So it's just our good old Gaussian probability distribution. And what we want to do is compute the amount of time that you spend at x equals 0. So you have to put x equals 0 in this formula and then integrate over all n up to the end of the game. And you see that because there's a 1 over square root of n in the denominator, when we do this integration, we get square root of n. So that explains why m is proportional to the square root of n. And so again, if there's of the order of 100 scoring events in a game, we'll get m equals 10 lead changes. But there's a very important but, and it turns out to be important, which is that basketball scoring is what's called anti-persistent. And what I mean by that is that when my team scores a basket, I have to give possession of the ball to your team. And what that means is that if team A scores, team B gets the ball. And if you then average over all basketball games, one finds the following statistically significant result, that after team A scores, team B scores next with a probability which is roughly 2/3, and team A scores next with a probability 1/3. This describes what's known as an anti-persistent random walk, in which if I step to the right, the probability of stepping to the right a second time is not 1/2, but only 1/3, whereas 2/3 of the time I step back in the wrong direction. So this property is called anti-persistence. And what this anti-persistence does is it basically renormalizes the diffusion coefficient by a factor of 1 minus p over p. And really, that's all there is to what happens. So I'm not going to derive the statistics of an anti-persistent random walk, but let me just tell you what the result is, because it's so simple, that if I have this anti-persistence probability p, that the number of lead changes is scaled up by a factor 1 minus p over p. And for these two factors, this is roughly square root of 2. So instead of having 10 lead changes, we'll have roughly 14. Another more sensitive measure is the distribution of the number of lead changes. And it turns out that if for a pure diffusion or a pure random walk with no anti-persistence, the probability that there are m lead changes in n trials of a random walk is just a Gaussian distribution. So the most likely number of lead changes is 0, but then it has this Gaussian tail associated with it. And if you then just include this correction factor for anti-persistence, you just renormalize the diffusion coefficient and you just get this factor 1 minus p over p, just propagating where n would be. And now we can ask, well, how does this compare with the actual game data? So what I'm showing you now is actual NBA game data with the red triangles. And so the black line is the most naive anti-persistent diffusion process prediction. And you see that it does a pretty good job. I'm sorry, I said this slightly incorrectly. The curve is just the random walk result. And if you include the effect of anti-persistence, then you get a much better fit to the NBA game data. And I want to try and stress here that the number of parameters that one has to fit here is one parameter, which is just this anti-persistence probability. So we can understand already some detailed statistical property of the game data in a very naive modeling. Now comes what I think is perhaps the most surprising aspect of basketball scoring statistics, which is how long does one team lead? So let's again look at our typical trace of the Chicago-Denver game. And we see that Denver has its leads almost the entire game, and then there's a few lead changes at the very end. So let's mark wherever Denver is in the lead. So when the score difference is positive, I'll mark with a green line. So here Denver's leading, then it's leading, and it leads at the end of the game. And what we're interested in here is the length of this green line compared to the length of the entire game. So that's the fraction of time that one team is in the lead. And what we want to ask even more detailed is what is the probability distribution of the amount of time that one team is in the lead? So if the teams are evenly matched, clearly this probability distribution, whatever it is, has to be symmetrical about 1/2. So I'm plotting the probability that the fraction of time that one team is in the lead that's the probability versus the fraction of time in the lead. So it should be a symmetric function about 1/2. And when I first came to this problem and I didn't know any better, I thought, well, look, the distribution has to be symmetrical. They're evenly matched teams. They're changing the leads very often. So it should be that most of the time, each team is leading 50% of the time. So my naive expectation was this. Doesn't that seem reasonable? You know, it's symmetrical. Each team is leading roughly the same amount of time. And it turns out that the data is exactly backwards compared to this. Here is the NBA game data. So instead of having a nice peak, one has a U-shaped curve. And moreover, which is, for those of you who know about random walks, you may not find this surprising, but I found it amazing. It matches perfectly something called the first arcsine law. And let me just mention a couple of things about this. First of all, this is a 0 parameter fit. There's no fitting anywhere. This is 1/pi is a known number, and this t is the total time of the game, and little t is the elapsed time that goes from 0 up to capital T. And one sees an almost perfect fit between the actual NBA game data and the first arcsine law. So this distribution of lead times is known as the first arcsine law, and it's one of the most beautiful results in the theory of random walks. And if you haven't seen it before, it's mind-boggling. And when you finally get used to it, it's still mind-boggling. So that's interesting thing. One interesting thing. The next thing, which is also amusing, is when does the last lead change occur? So let's look at a typical game trace. And so, you know, there's some lead changes, but there's the last lead change. And then the game ends where one team is leading by an amount X. And I want to ask, when is this time? When is this time? What is the probability distribution of this time? I want to compute this. And naively, I would have thought, well, if the teams are evenly matched, they're changing leads all the time, this last lead change should occur very close to the end of the game. So this should be a distribution that is peaked very close to the end of the game. So let's see if that naive guess is actually correct. So in order to have this being the last lead change, we must have that the score has to return to 0 at time t. So we must have a return then. And now, to understand, how do we understand this segment of the evolution of the score? So let's, instead of going forwards in time, let's go backwards in time. Let's start at the end of the game and go backwards in time. We start at some unknown position X, and it has to be that this trajectory has to come to 0 exactly at time little t. So this is what I would call a time-reversed first passage path that goes from X to 0 in the remaining time of the game, big T minus little t. So what I mean by a first passage path is that it starts at a non-zero X and comes to the origin for the very first time. So if, for those of you who are not familiar with these first passage paths, let me now do a bit of a digression to describe, well, actually, before I do that, let me just tell you what the mathematics is. So the return at time t is just the Gaussian probability distribution evaluated X equals 0. So it's 1/square root of t. And this object, I'm going to derive it momentarily, but here's the analytical expression. So for those of you who are unfamiliar with first passage paths, let me do a digression and talk about the occupation and first passage probability of a one-dimensional random walk. So for those who have ever been exposed to random walk, the very first thing that one learns about is where is a random walk? And that's quantified by the occupation probability, which is just our good old friendly Gaussian probability distribution in one dimension. 1 over 4 pi dt square root e to the minus x squared over 4 dt. But what I want to ask now is a somewhat different question, is that when does a random walk starting at some point x naught first hit the origin? How can we calculate this thing? And it turns out we can calculate this by a very simple device known as the image method from electrostatics. So let's look at a space-time plot of a random walk that starts at x naught at time 0, and it's going to propagate in time. And at some point, it's going to hit the origin. I want to ask, like, how do I compute the probability of hitting the origin for the first time? Well, the way that you can do that is to say, well, look, here is the probability distribution, but the problem with this Gaussian probability is that it also includes paths that might have hit the origin before this point here. And so we've got to get rid of those walks that hit the origin first. And the way you can do that in a very simple way is by adding an anti-Gaussian. You start with another negative image walk that starts at minus x naught. And if you sum these two things up, here is the original Gaussian, here is the image Gaussian. By symmetry, these two things add exactly to 0 at the origin. So this allows you, by this simple device, to calculate the probability of coming to the origin for the first time, because everything that came by earlier has been canceled out by this image Gaussian, image anti-Gaussian. So now that we have the probability distribution, we can compute the flux to the origin. And the flux to the origin is the first passage probability, because the diffusive flux to the origin, because of including the negative Gaussian, we only include walks that come to the origin only for the very first time at a given time. So the first passage probability is nothing more than the diffusive flux. And now you just do a simple calculation and you end up with this very nice formula, x over t cubed e to the minus x squared over t. This remarkably simple result has some amazing consequences. First point is you can ask, well, if I start at x naught, will I eventually hit the origin? And the answer is yes, for sure you will hit the origin. And the way you can see that is if you take the integral of this first passage probability and integrate over all time, you will find you get exactly equal to 1. So every walker that starts at a finite distance away from the origin, if you wait long enough, will certainly hit the origin. But the other thing which you can ask is, how long does it take to hit the origin? And what's amazing here is that notice that for a long time, this goes to 1. This is t to the minus 3 halves. When I compute the first moment, it's divergent quantity. So the average hitting time is infinity. So this dichotomy, you are sure to hit the origin, but the average time before you reach the origin is infinite, is what makes random walks so paradoxical, so beautiful, so important, and still so not fully understood. Okay, well, with this digression, now let's go back to our basketball story, and let's compute the probability distribution that the last lead change occurs at time t. So we have a return at time t. We have this time reversed first passage from x to 0 in a time big T minus little t. So here's the standard first passage formula. And then what we want to do is to integrate over all possible values of x, and then we'll get our answer. So let's do that. So let me call pi of t the probability the last lead change occurs at time t. So I have the return probability, the time reverse first passage, and then I have to integrate over all positions of the final lead. And there's a factor 2 because x could be either positive or negative. So this is an elementary integral, and lo and behold, you get the same formula again. And this is called the second arcsine law. In fact, there are 3 arcsine laws. Arcsine law 1, 2, 3. Arcsine law 1 is the probability distribution of the time in the lead. The second arcsine law is the probability distribution of the last lead change. And the arcsine law 3 is the probability distribution of the largest lead. And they're all the same, amazingly enough. So let's now compare this very beautiful formula with data. So here again is, and hopefully not a surprise anymore, it's a U-shaped curve for the distribution of when the last lead change occurs in a basketball game. And if we just do the homogeneous, if we do simulations of a homogeneous Poisson process, we more or less describe the curve beautifully. But we can do even more than that, because as we saw in the third slide of the talk, I believe, is that the scoring rate is not exactly constant everywhere through the game. And the homogeneous process is assuming a constant scoring rate throughout the game. But if we take an inhomogeneous process, Poisson process, where we take the actual scoring rate in each second of the game, we can actually account for all the little glitches in the data. So it seems like we really have got, we understand this very well. And here's the arcsine law. Again, no parameter to fit. So let me now come to the question, why are there two peaks in that distribution? Because as I mentioned a few minutes ago, I thought if the teams are evenly matched, the last lead change should occur close to the end of the game. So there should be one peak near the end of the game. So what I'm plotting now is the score difference as a function of time, but instead of using time as my variable, let's use log time. And the reason for using log time is I would argue that, you know, since we're dealing with a random walk process, which is scale invariant, we better use sort of a natural scale invariant time axis. So if we plot versus log time, and suppose the end of the game is here, then we see that the last lead change happened very close to the end of the game. Now let's take another example game. So this is just meant to be, you know, anything I just pull out of a hat. But here's another trace, and here the last lead change occurred here. But if we're on a logarithmic scale, we all know that if you just go a little bit back, you're already like down orders of magnitude. So this is already a lead change near the beginning of the game. You really have to work hard to get a lead change which is somewhere near the middle of the game. So either the lead change is going to happen very close to the end, or anywhere else in the axis, it's very near the beginning. So that's a sort of hand-waving argument for why there are two peaks. For those of you who want to be betting on basketball games, let me tell you how to bet. So you might want to ask, when is a lead safe? So in England, you know, they have real-time game betting, where partway through the game, you can say, well, I'm going to bet $10 that my team is going to win. So I want to ask then, let me compute the probability that a given lead of L points is safe when time tau remains in the game. So that's this Q quantity. So here we have a lead of time of size L, a time tau left in the game. How safe is this lead? So this lead, the probability the lead is safe is 1 minus the probability the lead is not safe. And the lead is not safe if starting a distance L away, I hit the origin before time tau. So this is the probability the lead is not safe. And 1 minus that is the probability the lead is safe. But this F is nothing more than our good old first passage probability. So we know how to do this calculation. We just have to write down, put in the first passage probability. And this integral is actually elementary, and you can do it right away, and you end up getting the classic error function as a function of the scaled lead change. So one consequence or one outcome of this description is that the lead change and the time tau are not two independent variables, but there's a natural scaling combination, the lead change divided by the square root of tau. So the probability that the lead is safe is error function of Z. So here it is. I'm plotting it as a function of the scaled lead size. And to give you a feeling for numbers, if you have a 10-point lead with 8 minutes to go, so if you put in 10 points with 8 minutes to go with the diffusion coefficient of basketball, one gets a probability that the lead is safe of 90%. So that just gives you a feeling for the numbers. And now let's look at the actual data. So here is NBA basketball data, and here is our very simple error function fit, and it fits extremely well. So again, the most minimal model is like a very good description of what's going on. If we were in the United States, I would say there's this very famous guy named Bill James, who is the inventor of sabermetrics and tried to metricize all aspects of sports. And he had his metric, and that's his metric, not very good, but he's much more famous than I am. Okay, so is basketball scoring a random walk? So I hope I've convinced you that with these additional results, the random walk hypothesis seems progressively more plausible. except there's some buts. So let's talk about the buts, because the buts are also extremely interesting and fun to think about. So the first one we've already discussed, anti-persistence. It's not basketball scoring is not a pure random walk process, but it's an anti-persistent random walk process. After team A scores, the same team will score next with a probability only about 1/3. And the other team scores next with a probability 2/3. But we've already seen how to take account of this by just essentially we're normalizing the diffusion coefficient. But now there's some more interesting buts. The first one is the last 2.5 minutes of an NBA basketball game. And these turn out to be completely crazy compared to the first 45.5 minutes. And I don't know how many of you have ever watched NBA basketball games, or especially NBA playoff games. But typically an NBA basketball game, the first 45 minutes will take an hour and a half of TV time. And the last 2 minutes will take like half an hour, 45 minutes, because they'll calling timeouts. They'll be doing deliberate fouls. There's a lot of foul shots. There's a lot of yelling and screaming. It's a completely different game. And let me show you how different it actually is. So first of all, let's go back to our third slide of the talk and look at the scoring rate. And originally I'd drawn a horizontal line around here, but notice there's this huge increase in the scoring rate in the last few minutes of the game. This increase in the scoring rate comes because even though the game is slowing down in real time, people are more desperate. They're trying, if a team is behind, they're trying to do desperate things to try and make up the difference. And this causes a rise in the scoring rate by a factor of 2. So another feature is, remember I showed you this growth in the variance, and I said, oh, it's a linear behavior. But notice that this linear behavior is dropping off in the last 2.5 minutes of the game. So there's something weird happening in the last 2.5 minutes of a basketball game. And to give you even a more clear evidence of this behavior, let's look at the probability distribution of the score difference at different times in the game. So what I'm plotting here is the probability distribution of the score difference as a function of the properly scaled score difference. So delta is the difference in score divided by 2 dt. So this should be something which, as time goes on, should be time invariant. And here d fit is the diffusion coefficient that comes from basketball, where we assume like a scoring, this happens basically once every 30 seconds. So at the end of the first quarter, we have something that looks pretty Gaussian. At the end of the second quarter, it looks pretty Gaussian, and we see nice data collapse. So we think, oh, we understand what's going on. Everything's a nice Gaussian random walk process. After the end of the third quarter, still the same. At the end of 45.5 minutes, almost still the same. So it looks like the first 45 minutes of basketball is described by a random walk. The last 2.5 minutes, something really weird is going on. And there's this huge peak at 0 because teams are playing for a tie. So if you're down by, 6 points, you try desperation 3-point shots. And if you make them, then you tie the game. So there's something outside the random walk picture that happens in the last 2.5 minutes of basketball. So all I can say about the last 2.5 minutes is that it's anomalous. Now, another thing, which nobody has mentioned, but is actually very important, is that there's a bias in this game because the teams are not evenly matched. They're not perfectly evenly matched. And in fact, when I give this talk in the United States, and especially when I give it at universities that had basketball powerhouses, this is when people would start yelling at me at the talk saying, it can't be a random walk because our team is much better than any other team. And so, it's not a random walk. And what I would like to argue, in fact, that even though there is a bias, the point is that the teams are not that unevenly matched. And why is that? Because when you get to NBA basketball, the very worst player in NBA basketball is 1,000,000 times better than I will ever be. And the worst player in NBA basketball has gone through many levels of filtration. He was the best player in his high school, the best player in his university, and maybe he ends up being the worst player on an NBA basketball team, but he's still an amazing athlete. So even though the there is a bias, it turns out it's not that much because of the fact that even the worst NBA basketball player is an amazing athlete. And as I'm going to argue for you that even though there are some differences, they won't matter. So let me try and argue that. So first of all, let's look at the role of unevenly matched teams. So, and in fact, let's look at this probability distribution of the time for the last lead change, which I showed was this second arcsine law. So this was true when the team strengths were equal. So you might ask, suppose the team strengths are not equal. What happens to this distribution? So here one has to work a little bit harder, but if you work a little bit harder, you find out that this arcsine law generalizes to this, more ugly looking formula. But here I'm quantifying the bias by a bias velocity v. So I'm assuming now that if the teams are unevenly matched, there will be a velocity v. So I can describe this by a biased random walk with a velocity v and diffusion coefficient d. And this is the probability distribution for the time for the last lead change. If you look at this quantity, so here is, I'm showing it now for 3 different values of the bias velocity, 0.002, and you see that the distribution is almost symmetrical. 0.006, it's very unsymmetrical. 0.004, which turns out to be the true bias of NBA basketball. So here what we do is we take every single game, we compute the score difference at the end of the game. From that, we infer a velocity. We then do that for every single game over 10 years, and we end up with a bias velocity 0.004. And so you see that, yes, indeed, there is some skew to this distribution of last lead changes. But then if you average over all the probability distribution for this bias, one gets back to a symmetrical distribution. And in fact, we even looked at what was the role of anti-persistence and if we have less or more anti-persistence. And you see that anti-persistence plays no role, and that when you average over the team strengths, then one gets back to a symmetrical distribution. So last point is the following. I call it return to zero. So the point is that if in a basketball game, a team gets a huge lead, then what they do is they put in their substitute players, they start goofing off, they don't take it very seriously. Whereas that if the team is behind, they are really grinding to try and make up the deficit. So if one looks at the scoring probability as a function of lead size, so if a team is ahead by 40 points, their scoring probability is 0.45, whereas a team that's behind by 40 points, their scoring probability is close to 0.6. So there is a restoring force that if one team gets a lead, in addition to just pure random walk, it's almost like, I guess the technical term would be an Ornstein-Uhlenbeck process. There is a spring which is trying to put the two scores closer together. So in fact, the true the true picture of basketball scoring should be anti-persistent random walk. I don't know what to do about 0.2. You have to include the bias, but that's easy to do. And one also should include this return to zero, or like this Ornstein-Uhlenbeck process. So let's do that. In the last few minutes of this talk, let me show you then what we tried to do is actually put all of these things together and make a computational model of basketball scoring in which we include all these different features. So our basic, so we're starting the basis of our modeling is what's called the Bradley-Terry model of competition. So let me first tell you what the Bradley-Terry model is, and then I'll tell you what we did. So in the Bradley-Terry model, you imagine you have a bunch of people who are competing, and each person is quantified by a characteristic quantity called their strength. So here are our elemental units, or teams. So let's call X alpha the strength of team alpha. And what is the output when two teams are on the basketball court? We want to ask, what is the probability that team alpha scores? And so in the Bradley-Terry model, it's just simply you take the relative ratio of the strength of A to the sum of the strengths, or the strength of B to the sum of the strengths. And this would be the probability that in any given scoring event, team A scores. And so in the Bradley-Terry model, they would just play this game where you had these probabilities PA and PB of team A or team B scoring, and compute the distribution of the outcomes. And they did some analysis of this. But what we want to do now is try and account for NBA basketball scoring statistics. So we want to augment this model by two features. One is the anti-persistence. So if I'm team A, then there is this extra factor because of the anti-persistence that if I've scored, then the probability that I score next, and by the way, this should be a minus or plus, not plus or minus. So if I score, the probability that I score next is going to be this Bradley-Terry relative strength minus 0.0152, and team B should have the plus 0.0152. So this correction factor is to account for this anti-persistence. But then we also have our score difference restoring force, which turns out to be a very small number. And so now we can do the following. We can say, let's take now a collection of 30 teams, which is what's in NBA basketball. We give them a strength X alpha according to some probability distribution. We play 1 million seasons of NBA basketball, and we will then compute some basic statistical quantities and compare this trivial model to what happens in the real game. So the only input in our model is the probability distribution of the team strengths. Now, because these scoring probabilities depend not on the actual magnitude, but only on the ratios, we can choose the average value of the team strength to be 1 with no loss of generality. So the only parameter is the variance. How spread out are the teams? So that's the only parameter in our model. So this is a busy slide. Don't look at everything at the moment. I'll explain it in just a moment. But here's what we did then. We took our computational model where we have 30 teams with strength X alpha that's Gaussian distributed with the variance of sigma squared. And then we play 1 million seasons of basketball and compare the results of our computational model with the actual data. So let's, for the sake of concreteness, let's look at the number of lead changes. So that's the red line. Forget everything else for the moment. So what I'm plotting here is, as a function of our only parameter, the width and the distribution of team strengths. I didn't want to do that. Yeah, so let's just look at the number of lead changes. So what I'm plotting is the deviation in the number of lead changes in our model compared to the NBA basketball scoring. And we see that when we plot as a function of the width of the distribution, that we get a minimum where sigma squared is somewhere, about 0.008. So again, for different sigma, for different values of sigma, the deviation between our model prediction and the actual data is going down, and there's a minimum so that we agree the best with the basketball scoring data at around 0.008. And now we look not just at the number of lead changes, but time leading, score difference, winning percentage, number of games you win as a function of your rank in the final standings of the NBA. And one sees that all of these very different statistical quantities have minima around the same value of sigma squared. So what we find is that if we look at the sum of these deviations or the product of these deviations, that there's a global optimum when we choose sigma x about 0.09, 9%. So the main conclusion from this is that if we choose a Gaussian distribution of team strengths with a width of the Gaussian 9%, which means that 2/3 of all team strengths are within 9% of 1, then the random walk model accounts for almost all the data, like any statistical quantity you could possibly imagine being concerned about can be described very well with this statistical model. So that brings me to the end of the story. Is basketball scoring a random walk? I say yes. Maybe you don't say yes, but I hope you'll say yes. And let me finish with Kamsa Amida. So I'm done.
Thank you very much. That was an outstanding talk.
Thank you.
And we have first one question in the chat box from Professor Kim.
Let me find the chat box. Hang on a second. Where do I find the chat box? Chat. Okay, here we go. Is there a way to say corruption of games if there's? That's a really good question. Excuse me. Yeah, I don't know. I mean, you know, again, the thing here is that our data set was roughly 10 seasons of NBA basketball scoring. You know, it's hard to say whether or not like someone is like trying to cheat in a game by not scoring very often, and you know how to decide was that like deliberate or was that just like someone that is injured or something like that. So I guess I have to say I don't know if this could be used as a way to detect some sort of corruption of the games, but that's an excellent question, and it's fun to think about it.
You know the
Yep.
You know the similar thing is happening in the Go game. You know the Go game?
In what game?
Go.
Go. Yeah. Okay.
You know now professional players are using this AI.
Right.
And they are cheating something
Yes.
by looking at the AI, so the prediction and all that.
Right.
So people are now investigating whether these guys are cheating or not by just looking at the games.
I see. Wow.
You may apply your method to the Go game.
Well, I mean, but you know, I think here, I mean, where I think you know there could be something useful is that in some sense, like but I mean, at a really fundamental level, one can ask like, why is there random walk description of basketball scoring in the first place? I mean, the point is that at least at the level of NBA, every single player has gone through many levels of selection. They were the best player in their high school, the best player in the university. They're well trained. They have a strength coach. They have a diet coach. They have a yoga coach. They have the coaches are very well schooled. They know all the the weaknesses and strength of all their players and all their opponents. And so I would say that in a situation like this, when the teams are so good and so evenly matched, you basically arbitrage away any systematic difference, because if some team has some advantage, people realize this team has an advantage. We've got to figure out a strategy to counteract it. And so that all that's left is random walk fluctuations. So I wonder if that might be the same thing if you had two AI champions playing Go with each other. Would it just be a random walk outcome? I mean, human versus AI, I guess now AI beats the human, right?
Yeah.
Yeah, but I mean, I don't know if you had two AI entities playing Go with each other. Could we describe that as a random walk?
Yeah, I had a question about this bias. So yeah, looks like, yeah, I kind of buy that the ballpark of this game is random walk, which
Right.
I think is why it makes it so like popular among people, because it's unpredictable.
Right.
But Sid, are you there?
Yeah, I'm here. I'm here.
Okay, yeah, you froze for a moment.
Okay, no, I'm here.
Yeah, but my understanding is that there is a team that wins for at least several consecutive years.
Right.
So if you like do this analysis for maybe decades, then it will be truly a random walk. But I guess what people are interested is during the short time interval.
Correct.
So
Yes.
I wonder if there is any way to tell from one season or a couple of seasons, one team won like for consecutive times, then can like give a PDF for that team winning again for the next and so on. So
Well,
that
I mean,
time,
yeah, sorry, go ahead, finish your question.
yeah. So I'm wondering if it's possible the tiny bias by
Well,
this
I
ball.
mean, I think that it would require, we only had 10 seasons of data. So I think we would need to have data that was extended much longer than a typical length of an individual basketball player career. But what I would say is you know, one thing about NBA basketball, and in fact, all professional sports in the United States, is that, you know, you've heard now in the past election, like Donald Trump saying, you know, we will never accept socialism. Socialism is bad. The Democrats are socialist. But in fact, all professional sports use socialism. The worst team gets best draft pick, and the best team usually gets the easiest schedule the next season. And the worst team gets the easiest schedule in the next season. So there's all these things built in to try and arbitrage away systematic differences. But you're absolutely right that there could be some interesting like relaxation to the equilibrium state. Like you could do the same kind of analysis one does, say, in the Ornstein-Uhlenbeck process, which is like, what is the correlation function, you know, as you relax back to the equilibrium point. So that's something which I think would require more data than we have, but it's certainly worth thinking about. By the way, I want to answer now the question from, here's another question. Have you analyzed other fast-paced sports like handball in the same way, or do you have any plans to study? So in fact, we also analyzed not fast-paced sports, unfortunately. We analyzed football, hockey, and baseball. And the problem with these sports as well, one is that the amount of scoring is much less. And so we only see the very beginnings of hints of random walk-like behavior. So, you know, if I could wait 10,000 years and gather enough data, I would argue that 10,000 years of ice hockey data might be able to then reproduce what we have for basketball. And the thing about handball is that, yes, it's a fast-paced sport, but I don't know where to find the data. That was one nice thing about NBA basketball data, is that it was actually easily available, easy to steal from the web, and we stole it, and we were able to analyze it. So, you know, it requires like someone who knows a lot about web scraping to actually get this kind of data. So I don't know, and I don't know too many other sports aside from football that has this well documented data. Okay, looks like someone's about asking another question here.
Let me have a question.
Yeah.
Thank you for your interesting presentation, Sid. You know, I try to understand your presentation in terms of a particular physical system, particularly in terms of Brownian motion. Okay, in terms of Langevin formalism. Just my speculation. If I'm wrong, just correct me. First of all, you argue that this is random work, but baseball is basically a mental sport. Of course, yeah, there is a sort of phenomenologically sort of random behavior, but my team is way way more bigger lead. Then I have less motivation to make a goal. So therefore, less motivation. Then as an anti-action, our opponent will have more motivation, catch up our team, and so. So eventually we will have a sort of random behavior, but it is based on heavily based on mental game between two games. So your analysis is basically phenomenological, right?
Yes. Yes.
Yeah, and then I try to understand, imagine your theory to, apply that kind of game into a specific physical system. So can I apply this in terms of, Brownian motion? I am a typical, harmonic oscillator, for example. I'm surrounded with many, many different teams. I'm described by other harmonic oscillators. So I'm now fluctuating. Okay, somewhat fluctuating, so to speak. Then eventually, my team will go a specific, particular the ultimate destination in terms of victory. Then my question is, I'm still wondering how can I get such kind of functionality in the environment of a random environment? Maybe my question is not that well defined, but in terms of Brownian motion, then there is a Kubo-Greenwood formalism, something like that, sort of fluctuation lead to functionality. Then here, in terms of harmonic oscillator, Brownian oscillator, for example, then I want to have a victory. Then that kind of functionality came from what? I mean, for example, you said anti-persistent, for example, that is the only reason or for that kind of particular, functionality, so to speak. Well, and again, you know what I'm saying? So I want to connect between the random work and sure some, non-trivial, the useful, function, so to speak, if you will. I mean, so
well, I guess what I would say is that basketball is very ideally suited for this type of analysis because the structure of the game is, roughly speaking, that there are these discrete events, basketball goals, and each of these goals is worth 2 points or maybe 3 points. And so the score is like undergoing some kind of a random walk process. If I call heads, team A scores, and tail, team B scores, it's just a sequence of these heads and tails with some amount of correlation between them that I tried to quantify and some degree of anti-persistence, but the overall picture is really nothing more than flipping the coin. And again, the reason why it's just so simple like this is that the two teams are incredibly evenly matched. You have incredible athletes, they have the same goals, they have the same training, they have the same diet, they have everything the same. And so all that's left when you put these two immovable objects next to each other competing is just random fluctuations is all that's left. That would be
Okay, then let me add one more question. Then if it is the case, then I know that to my understanding, of course, my understanding is limited, then the random motion, then what is, reasonable explanation leading to the arc cosine rule, which is very unique in this situation. I think is not necessarily often happen in typical generic physical systems. So what is then deciding role which lead to this the arc cosine rule?
Well, so look, I think the point with this arcsine law is that this is one of those things which when I was first learning about random walks, and the very first time I encountered the arcsine law, I said, I cannot believe what I'm reading. This has to be wrong. And I was out of Feller's book, so obviously it was right. And the point is that, the random walk model is like incredibly simple to state, but it has some incredibly subtle features like the arcsine law. So it requires nothing beyond just pure random walkology to give you this arcsine law behavior. And the reason, if you want to try and argue like why is that the case, it's just that if you think about a random walk of t steps, the number of times you pass through the origin is only square root of t. And so that means that there's large periods of time where one team is leading or one team is losing. And this is the basic mechanism that ends up giving rise to the arcsine law. It's that there's square root of t lead changes in a time t. And the most probable event is no lead changes in a time t. That is the most probable event. And this just comes from the statistics of pure random walks.
Okay, thank you.
Sure.
I want to ask one more question.
Sure.
Can I? Yeah. The basketball is a highly interactive system, game.
Yes.
So maybe so I want to ask whether the randomness, horrendous randomness, comes from this the interaction among the players. And if it is the case, then is there any analysis for the very interactive games like golf? I mean, in this sense, or marathon, and two teams are splitted in the what is it? What is like a ping pong ball or something like that.
Right.
So some games, even though the team competition, there are some very non-interactive games. So is there any analysis, or can you guess what?
Well,
what
I mean,
might be different?
let's talk about the least interactive, or one of the least interactive games, which is golf. And there, people have done various sorts of analyses of like what is the distribution of scores at the end of a tournament, and like and I guess the thing is that So again, it's like there's not a random walk picture there, but one can use ideas from stochastic analysis because one can say, one can look at the probability distribution of like where the driver, where the tee shot lands, where the second shot lands. And so people can build statistical models of like, what is the score distribution in golf? I guess the thing I would say there is that it's, to my mind, it's not as clean and not as simple as like basketball, which is interactive. And so because of the interactivity, it's just that, again, all systematic differences are kind of arbitraged away and all you're left with is random fluctuations.
Yeah. So still there are a lot of random sources.
Yes, absolutely.
Yeah.
So here's another question. Can we attack this problem using extreme value statistics? For example, the distribution of the largest score difference and its relation to the parent distributions. So I guess what I would say is that's an interesting question that I don't know fully the answer. What I can tell you is that when the largest lead change occurs is known, the distribution of the times for the largest lead change is described by the third arcsine law, which is still 1 over pi times 1 over root t, capital T minus little t. But the actual magnitude of the largest score difference, I have not thought about that, and that's a good question. And whether or not like it fits within the framework of extreme value statistics would be interesting to investigate. So good question.
Any other questions?
Well, thank you for your attention. I find this a very strange experience, like to just talk to a bunch of little boxes on my screen. At least two of the boxes are familiar faces, so at least I made it a little easier.
Changbong, do you have any?
No, I enjoyed your talk, and then yeah. So I have maybe one question. So this is like a the emergence of this Gaussian distribution or whatever, which give rise to the actually this random walk is initially the statistics is the binomial statistics, right? And then for certain approximation, like a very large n and some finite p, you have some Gaussian, and also some of random variable, IID random variable should be like leads to Gaussian distribution. And then you are asking some specific question, how long does the one team leads, and that kind of question actually give rise to the arcsine law, right? So I mean, but if you look at some physical phenomena, sometimes we don't actually get the Gaussian distribution. I know maybe the assumption is not actually valid there, like a large n or some finite p. So like for instance, a polymer looping problem. I mean, Gaussian polymer of course leads to like a Gaussian some sort of first looping time is like 1 over t to the 3/2, but persistent I mean chain semi-flexible chain doesn't actually give rise to the kind of looping time statistics. So when do you expect that this kind of law actually deviates from this your Gaussian distribution actually? So it's not large or something like that?
No, so yeah, I mean, but I guess what I would say is that, like, let's talk about the case of the semi-flexible polymer chain, your specific example. So there is a persistence length associated with the chain, which is that, when it sort of forgets the direction that it's going in. So, in some sense, like in the good old random walk, you'd say that when the number of steps n is large, you could go to, the continuum limit. What we need for the semi-flexible polymer chain is that when the number of persistence length and the length of the chain is large, when that is large, then we go back to like the usual Gaussian behavior. But if the persistence length is 100 units and the length of the chain is 200 units, then of course we are not anywhere near that asymptotic limit. And the thing is that if you're dealing with things like the persistent or anti-persistent random walk, I mean, the more careful way of describing it is, first of all, you have to start with the discrete recursion formulas. But when you try to go to the continuous limit, you end up with the telegraph equation, which has another term in it, which is related to like the sort of comparison between the persistence and the overall length of the chain. And so one needs to include that if one wants to deal with something where the persistence length is long or is like a finite fraction of the total length of the system.
Mhm.
Yeah, I think, let me just add, there is a, when you take the central limit theorem, you take log of the binomial distribution, then apply Stirling's approximation. So I guess the accuracy of that continuum limit depends on whether you can, how much you can suppress the third order and higher order terms.
Mhm.
Yeah, that's exactly right. I mean, and again, there's books in probability theory that talk about like how large n has to be before, these terms are suppressed, and like how much are these higher order terms suppressed by. And so one can make a really clean criterion for when you can go to the, continuous limit and the Gaussian limit.
No other questions? Well, yeah. I personally enjoyed your talk a lot. It's
Well, thank you very much.
amusing, and I think other people had the same impression. And
Okay,
yeah.
well, thank you for the invitation. And one of these days, I hope I'll see you like, for real rather than like, in these little boxes.
Yeah, very much. Yeah, certainly.
Okay. Okay.
Thank you very much.
Bye.
All right. So long. Bye, everybody.
Bye.